Hey everybody, Lars here. Because I gave you an oldie but a goodie for video 1, this is video 2 for Unit 4. We are going to take a little time. I don't want to go forever and I don't want to bore you, but I don't want to go so short that you don't get anything out of it either. So we're going to look at a couple of different aspects of the topic of recursion, what's in the middle of Unit 4. Now, you know, because you've listened to the spiel a couple times now, how I extract the computer science stuff when I teach initial programming. I give you the basic skills, and then I bring the computer science back. So now you can see searching and sorting and recursion and big O and stuff like that. Recursion is often considered one of the harder things to wrap your head around in computer science, but I've always wondered why, because I think if you approach it properly, it's not hard at all. It's just a different way of doing what you're doing anyway, and you're going to see that as we go through things. So at first, what I usually do is I pop up the recursion Wikipedia page, and what you find is that recursion happens in a lot of different places. It's not just computer science. Here you have in advertising, you have the Drost cocoa can, where the nun has the tray, and on that tray is a Drost cocoa can with a nun with a tray, and on down the line. It's almost like looking down, with mirrors. Okay? Basically, at the end of the day, recursion is talking about something that's self-referential, something that refers to itself. And if you know anything about the history of mathematics, that kind of gets us in trouble. Okay? So we've had to think about and learn about different ways to handle it. Also, you see a snake that's eating its own tail. In culinary situations, recursion occurs because when you make sourdough, part of the recipe is to use a piece of the previous sourdough. Okay, now that begs the question, what happened the first time you made sourdough? But a lot of sourdough recipes call for a piece of the previous sourdough. Okay, so that's kind of recursive. You've got to refer to yourself in the recipe, so it's a little weird. But later as we go down, we'll see Sierpinski's triangle, and we'll see how recursion is handled in mathematics and in computer science, because at the end of the day, computer science and mathematics are basically two sides of the same coin. Okay, in computer programming, basically what we're talking about is something that's self-referential. And I always tell the story, and I always do it this way. When you're 19 years old and you go to university for computer science, like I did back in the 80s, they teach you recursion with two different examples. One is Fibonacci, the Fibonacci sequence. You get 1, 1, 2, 3, 5, 8, 13, on up the line. It's just the number is the sum of the two numbers before it, okay? And you can do that recursively. Or you can do something called factorial. Like factorial 5 is 5 times 4 times 3 times 2 times 1 on down the line. I think it's 120. And then you can do more numbers, okay? There are ways to do that with recursion. But the problem is a lot of 19-year-olds, including me, when I first hit college, I was no super genius. I was no great shakes. I was a smart kid, but I wasn't a genius. I had never seen Fibonacci and factorial before. So when I saw it done with recursion, I relate the operation to the technique. I'm thinking, oh, that's the way you do factorial. That's the way you do recursion. You don't necessarily think of the technique as something different from the way you've been doing things, which is why when I do recursion, I usually use operations that you know already, that you're already familiar with. So if I'm going to do addition and then I'm going to do multiplication, because you know how to do that already, the contrast is going to be in the technique. And then you're going to be able to say, oh, okay, that's what recursion is about. I've always said using factorial and Fibonacci, you're showing someone something for the first time. They're going to relate it to recursion, and the technique isn't going to stick out. Okay, so I'm going to show you sums, and I'm going to show you multiplication, and hopefully the technique sticks out, and you say, oh, okay, I've got to look for situations where I could take a list and make it smaller. You're going to learn what I'm talking about as we go. So the first thing I'm going to do is I made some code up already, but this is no great shakes, as you're going to see. I say messing with recursion. Now, I'm going to code it up, and I'm going to run it, and then we're going to trace it. So don't worry if you don't understand as I code it up. Basically, all I'm going to do is I'm going to create a function. I'm going to call it my sum, and I'm going to take a argument n, okay? And then I'm going to say if n is equal to 1, then I am going to return a 1. And you'll see what we're doing when we get there. Then I'm going to say else return n plus and then I'm going to call the function again. And this is where it gets weird because look, I'm creating this function, but I'm calling it inside of itself. So this is where the confusion comes in, and this is where people think it's weird. I'm done already, okay? And we're going to see what happens in a second. Then I'm going to say print, and I'm going to say print my sum, let's say of 5, okay? So what's going to happen? Well, let's run it first and see. All right, I get a 15. Let's get our trusty, dusty little area where we can see things together and talk about them. Let me put it over here. All right, good enough. Hopefully I'm zooming in and we're all good. Now, what happened here? Well, I came into the program. I ignored my comments. I loaded my function, because we all know about functions now. I loaded it in memory and didn't really run anything. Ignored the comment. As happens sometimes, the first thing I run is literally the last line. So I do a print function, and inside of it, I call a function my sum of 5. So I come up here, and I say my sum of 5. If 5 is equal to 1, it's not. So I do the else. Else return 5 plus my sum and minus 1, which is 4. Okay? So now I run it again. But this is where the confusion comes in. Then people will come up here and say, okay, my sum of 4 is 4 equal to that. No, return else. But wait, didn't I have a 5 there before? And didn't I do some other? People get confused because when you trace code, you use what's in front of you, and you're trying to reuse this when you just ran through it, and people don't like it. It's weird. Okay? What you have to do, and what we're going to drill home in the next example, multiplication, is think of it just like the computer's handling it. Don't come up here and start reusing things. Think of it as a fresh, blank copy off to the side, because that's exactly what your computer is doing. It's just grabbing another copy from memory. When you recall it here, the computer doesn't know any different. The computer's not looking at it the way we're looking at it. The computer says, oh, okay, grab another copy of that. So it grabs a blank copy of this. So when we run through it, it's like, think of it as a blank copy off to the side. And when I do multiplication, you're going to see how I chart it out. You're going to see what I'm talking about. All right. So then I've got return 5 plus my sum 4 minus 1. So I run it again. And what do I get down here? Return 4 plus my sum of 3. Return 3 plus my sum of 2. And I go down the line until I get to the 1. When I get to the 1, I return a 1. Where do I return it to? Here. So I get 1 plus 2. That equals 3. I return it to what? The one that called 3. So I get 3 plus 3 is 6. What do I return that to? The one that called 4. 4 plus 6 is 10. What do I return that to? The one that called 5. 5 plus 10, 15. Okay? If I did it with 6, you would see I would get, how about changing it to 6 first? You would see that I'll get 21. Okay? Because it just adds the 6 to it. And it keeps going until you get to 1. All right? So that's all it is. Think of it as a new, fresh copy. Now, and this is the trick I like to do, because I like to, when you're taught factorial, that's all factorial is. Change the plus to a multiplication. So now, and I'm going to give this to you as my sum, so I'm not going to change the names. But you could, well, you know what. Let's say I called it my fact. That's it. That's really all I have to do to make this factorial. So now if I run it for 6, it's because I'm not calling my fact down here. So now if I run it for 6, you see I get 720. I'm running off my screen already. I'm going to make sure this whole screen is there for you to see. Okay, so I get 720. All right, that's factorial. Now I'm going to change it back to sum before I give it to you. All right, but this is where I usually bring up something. Hey, if you're watching this video, you're doing the right work. You're about to catch a break, because I'm going to tell you for a fact in your Unit 4 quiz, you're going to be asked to code up a factorial function, okay? And I don't know why this happens, but a lot of people will not look for 1, but they'll look for 0. I hope it's not people cheating off other students, or somebody has an old copy of code or something like that. And this is the thing. I just ran that code, and I got 720, right? I changed that from a 1 to a 0. Now I rerun it. What's going to happen? The same thing. Because if you look at what you're doing with multiplication, what's going to happen when you strip that down to 0 and you go through again? You're multiplying by 1. I always say it, and I don't think anybody's ever given me, there's never a reason to multiply by 1. Why? Why? You already have the thing you need. What possible reason could there be to multiply by 1? You're not cleaning anything. You're not doing anything. Somebody has yet to give me a reason why you would ever multiply by 1. There's no reason why. You have what you have. You have what you need. You're not changing anything. Okay? So that's kind of inefficient. When you go in factorial and you're shrinking a list and you want to get down to what we call the tail condition before you go up the stack and add or multiply everything, you want to look for 1. You don't want to look for 0. All right? So you heard it here first. I don't want to see any zeros when we do the Unit 4 quiz. All right? So basically, that's how it works. What you're doing technically is you're finding something that needs the same operation done over and over again, and you can just shrink the list until you get to 1, and then go up the stack and do whatever the operation is. Here, we're going to take a list of 6, and we're going to 6 times reduce it down to the lower numbers, and then as we go up the stack, we're going to do the operation. We're going to multiply. All right? So what I'm going to do is I'm going to change this back to my sum, and I'm going to change this back to my sum. And I'm going to change this back to my sum. And what we're going to do is change that multiplication to an addition. And we're going to rerun it. And it's going to say 21, and we're going to be happy. I'm going to put that code up on Sakai for you. Okay? But in keeping in what we're doing here, I'm going to show you another example. But I'm not going to show you Fibonacci. I'm not going to show you factorial. You just saw factorial. All right? I'm going to put sum up in Sakai, and we're going to take a look at multiplication. Let's SOTS that out so we get something fresh. And then I'm going to grab my multiplication. All right, so that's not multiplication. Here's multiplication. All right, so now we're going to look at multiplication. And you can see this is how I do multiplication recursively. First I do mult3 of 3. I'm going to run it. And we're going to see that it gives us 27. Which it shouldn't, so I'm going to have to see what's going wrong. That's what's going wrong. You should note what just went wrong for your assignments. Enough said. Why is that doing that? That is annoying. All right, so now when I rerun it, I get the answer, which is 9. Okay. I call my mult3 of 3. I come up to my mult. Num is 3, times is 3. Is times equal to 1? No, it's equal to 3. Okay, so I do the else. Return num, which in this case is 3, plus my mult 3, and then times minus 1, which in this case is 2. And then I would call it again, but now we go back to our old example, where I'm coming back here and I'm reusing the code, and it's very confusing, and it's really crazy. So as we do this, we're not going to do that. What we're going to do is this. Okay? I'm sure with the magic of Camtasia, I have zoomed into the proper spot, and you are going to forgive me, because sometimes I have a tough time when I draw these numbers. We have def my mult. We're going to start from scratch. So I gave it a, not bad. I gave it a 3, and I gave it a 3, right? If times is equivalent to 1, it's not, it's 3. So else, return num. What's num? Num is 3. My mult of num, which is 3. Times minus 1, which is 2. All right? And now's the trick. I'm recalling this function. So where do I want to go? I go to a brand new, fresh copy. So what's the num here? The num is 3. What's the times here? The times is 2, because that's how I called it. Okay? Is times equal to 1? No. So else, return num. What is num? Num continues to be 3. And my mult of num, which is 3. Times minus 1 is 1. Okay, so I call it again. And where do I call it? Another blank copy. Only this time num is 3. And times is 1. So, if times is equivalent to 1, is it? Check. Yes, it is. So I return num. And num is what it's always been. It's been 3. Okay, so where do I return 3 to? Return it to up here where the function call was. So this entire function call right here came back 3. So now I'm ready to do the return here because I return num plus 3, which is 6. Okay? Where do I return that 6 to? Up here where the function call came from. So all this in here, my mult, whatever, came back 6. Okay? So now I can return this. Num 3 plus 6 is what? 9. Okay? Now, where do I return that 9? Right here, where I called it. So A is assigned 9. I print A, and what happens? 9. Okay? As you can see, when you look at that, this looks crazy right now, but you saw the trace and you know what I'm talking about. What would happen if we did 3, 4? Okay? What would happen if we came in here and we changed times to a 4? Okay? We rerun it and we get a 12. Because what are we doing? Every time we do this operation, we're adding 3. That's all we're doing. We're adding 3. You could see it as we went up the line. So I did a 4. We would just do this another time. We would do it a 4th time because every time we're doing it, we're adding the 3. And it makes sense at the end of the day, right? Because what's multiplication? It's addition on steroids. Okay? So that's what we're doing. Where every time we do it, we add that particular number. Okay? So soak this in, because I don't think I take this diagram and upload it to Sakai, but you're going to get the code. I'm going to give you the multiplication code. That's it at the end of the day. This is how we do multiplication recursively. Okay? So what are we going to do? We're going to recognize that multiplication is a series of additions. So we're going to do the additions as many times as we need to do it. So what we do is we take one of the 2 operands for the product, and we reduce it down until it gets to 1, and then we come up the stack and do the addition operation. Okay? That may sound confusing and mathy right now, but it won't. In the future, you'll get it. Okay? And soon you'll look for operations which lend themselves to recursion. It's like, oh, that's the same operation repeated a lot of times. I just want to do it and make my list lower until I get to 1, and then you come up the stack and you do it. And that's how, in a computer science way, that's how we handle a lot of problems. You're going to see down the line, there are going to be a lot of operations that lend themselves to being attacked recursively, like searching binary trees. You're going to learn about binary trees, and you're going to say, oh, what's off to the side? Another binary tree. What's off to the side? Another binary tree. So you're going to see if you can create recursive functions to work on structures like that, that you're well served. You're in very good shape, okay? Because in a lot of times they're very efficient. All right. So at the end of the day, recursion, simply put, is an operation that's self-referential in a sense. But once you get used to it, and once you get used to seeing things that have recursive solutions, that light bulb's going to go off in your head. You're going to go, oh, okay, I get it. And now I see what's going on. And you can do, there's a whole bunch of different things you can do with recursion. As you look in the Zell book, you can see there's a bunch of examples in there that do things with text and finding different combinations of numbers and things like that. Okay? All right, then I'm going to put the summation code and the multiplication code up on Sakai for you, as well as the link to this video. And you're going to have that to look at. And as usual, this is YouTube. You want to see the trace again? Watch the trace. Look at what the numbers are. See what we're doing. Because at the end of the day, recursion doesn't have to be hard. You know, a lot of people go, oh my God, that's crazy. It's not. It's only crazy if you try to trace everything in that one piece of code and you make yourself nuts. And then you think you have to be a super genius to remember what everything was 5 levels down. You know, you go get a blank copy, you use it. You go get a blank copy, you use it. That's it. You have to make yourself nuts. All right? So I'm going to leave all of that stuff up. Now, announcements. We are in pretty good shape. Unit 3 just ended 2 days ago because I'm doing this Sunday right now, Sunday, July 8th. Summer's almost over, guys. Think about it. I mean, in 5 weeks, I'm going to be setting up for fall 2018 over in the cave. That's it. Summer's going. We're officially more than halfway through this Python course. It's crazy how fast this summer went. Well, because I was moving. And now I'm a little more calm because I'm here in the new digs in New Brunswick over at Colony House. So the house, I closed on the house Monday the 2nd, all done. I cleared out my storage space. I gave it back, all done. So now the only 2 places I really have my junk are here in the apartment and over in the cave in my office over at Rutgers, which is good because it's all here in New Brunswick and it's all closed. So I'm waking up every day and not knowing what to do with myself because I don't have a list of 17 things that have to be done. Moving is a pain in the ass. Woo! It's crazy. I still have a lot of places that I have not changed my address, my driver's license, my life insurance, my medical, my dental over at Rutgers. I've changed a lot of stuff. I've changed like all the credit cards, all the bills when I canceled them for the house. I did a bunch of that, but there's still so much still to do. But it's all paperwork stuff. It's not crazy stuff. My TV died on me. I bought 2 TVs and had Geek Squad come put them on the walls for me. And the little one, the 60-inch right across here, died. Geek Squad, good God. I called them up and said, hey, I need, I'm still under the warranty. Can you come replace the TV? They said, yeah, we'll come out on the 20th. 2-week wait. Not good. Not good. But they have a gun to my head because I had them put it in. I don't have any choice. I'm not going to take it down off the wall and bring it over there to return it myself. I'm not doing that. So they say, yeah, we can send someone out the 20th. I'm like, that's shitty. You got to hire more guys and girls. You got to hire enough people so that if people need a repair, they can get it within 2 or 3 days. They don't have to come out within the hour. I'm not crazy. But 2 weeks? 2 weeks is ridiculous. And believe me, I'll tell them so. I will be a real irate customer when that happens. So now basically, like I said in a review I did on Sony online, I may as well have had a dead deer put on my wall because it's useless. It's just sitting there for 2 weeks and it's useless. And I paid for it. And who's going to give me that money back? The 2 weeks I didn't get out of it. I digress. I apologize. I don't mean to go down this rabbit hole. But it's a pain in the butt. That said, if that's the only thing that goes wrong with this whole move process, I'll take it. I'll take it all day long. Because it's not that big a deal. It's not going to cost me anything. And I have 2 TVs. It's not like I can't watch TV. I can go watch the other one because I'm a spoiled brat. So at the end of the day, it's a small thing. All right. Announcements. You're doing great. Kit right now is going to grade the assignments and the quizzes from Unit 3. I'll probably get them to you sometime late in this coming week. We have class on Tuesday on the 10th, so be aware of that. Go to class because we're going to go over the harsh ed assignment. Some people had a little trouble. I think the trouble is because you don't engage with, and I sleep well at night because I warned you at the beginning that it was going to be a long process. And then some people picked it up after a couple of days. They said, oh my God, I can't do it. Well, it's because you didn't engage with the resources early. You got to engage with the resources early. All right. So we're going to go over that in class and you're not going to have any issues. When I am done shooting this video, today's the 8th, I'm going to sit down and I'm going to create groups. So you're going to, by the end of today, you're going to have groups and you're going to have an announcement talking about groups. All right. So you're going to be set and you're going to be able to sit and talk and discuss things with your group mates because I'm going to hopefully leave you an ample amount of time at the end of class on Tuesday. And you can start getting going on what you need to do as far as the final project is concerned. Also, be aware that in 4 days, the midterm is due. All right. If you're a day late on the midterm, I'm not going to care. But don't say I need another week with it. Get going. All right. Because the midterm paper, it's only a 5-page paper. It's really 2.5 pages. And then you double space it. And all right. So get going on that because that, I believe, is due the 12th. Okay. Which is 4 days out. I think it's Thursday. All right. So you should be good on that. Other than that, everything is good. I know it's truncated during the summertime. It makes me crazy too that we have to go so fast and we have to do all of these things. But, it's summer, and in 11 weeks, you're going to get done the same amount that other people got done in 15, and you're going to get the 3 credits over the summer, which is always awesome. It's always a good kick. So you'll be rewarded for your hard work. No worries. All right? Then I am going to get out of here. Don't forget, we have class on Tuesday. Tomorrow night, I will probably drop the assignments for Unit 4. So you will have all your resources because this is a 2-week unit, 10 days for you guys, where you get your slides, your Zell, 2 review videos, the oldie but goodie that I sent you yesterday, and this recursion video. And then I'll get you the assignments with a week to go in the unit. Unit 4 is usually a respite between Units 3, which is the 3-weeker, and Unit 5, which is a 3-weeker, okay? But as things get going near the end of the summer, you're going to be doing Unit 5, Unit 6, your final project. It's going to be busy as far as Python is concerned. So like I say, way at the beginning of the course, do it for a half hour or 45 minutes every day. Don't say on Saturday, I'm going to do 4 hours. It's a crappy way to learn. You can't learn it that way. You're not going to, because you're going to run into problems and you're not going to have time to go away for an hour and think about it and do all that and come back to it. And this computer programming lends itself to success when you do a little bit every day. It's not something you can cram once a week and get good at. You need to practice, 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 practice. You need, and this goes in I study gaming and education. And one of the things that gaming helps with is that you learn to fail. You learn how to handle failure, okay? Cycles of expertise. You try again, you try again, you try again. As you try, you light up more of the problem space and you start to understand the problem better. Then eventually you have success. That's the way we learn. The way humans learn. We do that. We do trial and error and we mimic. That's the way psychologically humans learn, okay? So when you have something to learn, try it, fail, try it, fail, try it, fail, try it, fail. You're going to learn more about that domain, that problem space, and then you're eventually going to say, oh, okay, this works because of this. And when I fail, it's because I did this. I don't do that anymore. Now I do this and I succeed. That's how we learn. So in a computer science context, you have to try things, a lot of things. You have to mess up. You have to correct your mess ups, okay? That's why learn the hard way makes you type everything in, because when you type everything in yourself, you're going to make a mistake. When you make a mistake, you have to correct that mistake. In order to correct it, you have to understand what's going on. Mistakes are good, okay? They are food for people who are learning. So that's what you want to do. Tons of examples, all right? Other than that, you're in pretty good shape. I think everybody is in with the assignments and everybody is in with the quizzes for Unit 3. So Unit 3 is put to bed. We're good and we're done with that, okay? We're on to Unit 4, all right? But you've only got 10 days. You got to do both of the assignments. You got to study up to do well on the quiz. You've got to read the Logic Named Joe and do your forum post. So as usual, it's summertime. There's no rest for the wicked. You got busy stuff to do, all right? All right, good. Then I'm going to see you in person in a couple of days on Tuesday night over at Beck. And we'll go through the Harshed and we'll have some fun. And then you can meet with your group mates and you can start talking about a little bit about the final project. All right? All right, then you be good. And I will talk to you later.